The second application of quantum mechanics, which we will discuss here, is the particle encountering a potential barrier. In this, a particle with energy E encounters a region of potential U0. Clearly, U0 is greater than the energy of the particle. Classically, if this is the situation, the particle cannot enter or cross this potential region, and the only possibility is of the reflection. So the potential region is called classically forbidden region or the potential barrier. U0 may be called the height of this barrier. Let this region extends from x equal to 0 to x equal to L. We shall call L the width of the barrier. Mathematically, this can be written as this. We wish to find what quantum mechanics predicts. For this, we need to find the wave function of particle in three regions: region 1, region 2 and region 3. Here, regions 2 and 3 are classically forbidden. The starting point is time-independent Schrödinger equation. In all three regions, time-independent Schrödinger equation can be written as this. Like what we did in case of particle in a box problem, we write the multiplier of second term as square of some other number for the ease of mathematics. Time-independent Schrödinger equation in all three regions are these. Here this term and this term can be written as k1 square, but this term cannot be equal to the square of any number because this is negative. E is less than u0. So let it is equal to minus k2 square. The solutions of first and third equations can be written as linear combinations of exponential terms representing the wave, like this psi 1 solution of first equation and psi 3 the solution of third equation. The second equation can be written as this, and so solution of second equation cannot be written as a combination of any wave equation. So psi 2 is any coefficient times exponential k2x plus another coefficient times exponential minus k2x. Here there is no iota, means there is no wave in psi 2. Let us talk on these solutions in more depth. In region 1 solution, the first term is the wave traveling along positive x-axis and the second term is traveling along negative x-axis. So this is the first term and this wave represents the second term. Let us read these solutions as psi 1 plus and psi 1 minus respectively. The region 2 solution is this. We shall talk about it after the solution 3. Like solution 1, we write solution 3 as a linear combination of two wave functions. Here, the first term is the wave traveling towards right. This represents a particle which have reached the region of transmission. The second wave would represent the wave or particle traveling towards left. But as we fire the particle from left only, the second term must vanish in solution 3. So this is not a solution. Let us return to solution 2. Its first term is an increasing function with x, which is not the case surely, and the second term is decreasing term indicating that the number of particles is decreasing as one moves in the barrier. So the first term vanishes and the second term is the solution in side 2. Here, what we see in contrast to classical mechanics is that the region which was forbidden in classical mechanics, this and this, do have some of the particles, and the region where no particle could reach classically do have a non-vanishing wave function. If we talk about the probability of particle reaching the region 3, then we need to square the solution 3. So the probability of transmission is directly proportional to this, where K2 is given by this thing. This T is known as transmission probability. As a summary, for a particle encountering potential barrier, quantum mechanically there is non-vanishing wave function in the classically forbidden region. The wave function in all the three regions are these. One thing is to be noted here that k values in incoming solution or outgoing solutions are the same. This represents that the energies of the incident particle and the transmitted particles are the same. The only difference is in the number of particles or in the amplitudes of the matter waves. The amplitude of matter wave represents the number of particles, and that difference in the number is given by the transmission probability T. It can also be concluded that T is the function of U0, E, and L. It decreases with increase in L and U0, while it increases with increase in E, and it becomes unity when E equals U0. This is known as the phenomena of tunneling. It is analogous to this picture that if there is a trolley which starts from this height, then classically it should not reach a point higher than this point, and therefore this trolley cannot cross this hill. But quantum mechanically, this trolley can cross this hill even if the energy of this trolley is not enough to cross the hill. Classically, this is possible only if this person digs a tunnel through the hill, and that's why this phenomena is known as quantum mechanical tunneling. We can talk more about it. In classical picture, if an electron has less energy than the electric field, then it will hit the barrier and will get reflected. But quantum mechanically, an electron is represented by a wave, and there is certain probability that it can penetrate the barrier and tunnel through it. A practical instrument which depends on the tunneling phenomena is scanning tunneling microscope. The STM is an electron microscope which is used to achieve atomic resolution. It is used to probe surface morphology. As you have studied that if the barrier width is small, then electrons from one side of it can tunnel to another side, even if they do not have enough energy. The number of electrons on the other side, or simply the electrical current, is directly proportional to the tunnel probability, which is related to the barrier width. An STM uses a very fine conducting tip. This tip is so fine that only a single atom is at its tip. A potential is applied between this tip and the conducting sample. When this tip is held very close to the sample, then depending upon the spacing between tip and the sample or the transmission probability, a current is drawn. By measuring this current, one can calculate the distance between sample and the tip. In this schematic, you can see here at the first point where the gap between the tip and sample is very large, a very small current is found. At the second position, where the gap is very small, a large current is drawn. And for a moderate width, a moderate current will be drawn. The drawn current is shown here. Less intense is the less current. So, to give a constant current, the tip has to be raised and lowered on the surface. So, by moving the STM tip, one can know the information about the geography of the surface or the surface morphology of the sample. Now, we need to move the tip to every point of the surface. This is known as scanning, and record the heights of the tip corresponding to each point for constant tunnel current, and then plot these values against each coordinate of the surface. This is known as constant current method or mode of the STM. There can be another mode also. in which the height of the tip is kept constant and the varying current is measured. Then calculations give the morphology of the surface. And STM is used in these two methods or these two modes.